Hello everyone and welcome back. Today we're going to start talking about multi-object systems. In this video, we're only going to deal with the most basic of these types of systems. But what's going to be important today is the technique that I show you, because the technique I show you is one, extremely vital for the course, and two, works with any multi-object system. So here is our setup. I have two objects, mass 1 and mass 2. Mass 2 is being pulled by an unknown force, which I've simply labeled force X. This could be from a rope, it could be another tension, it could be someone pulling it, it doesn't matter. Whatever it is, I'm simply labeling it force X. So you're typically asked a few goals. One, you're almost always asked to draw a full force diagram of the system. That means properly drawing and labeling all forces. Second, you are typically asked to find the acceleration of the system. And third, notice I have a rope here between mass 1 and mass 2. This rope obviously will have a tension, which I will call T1. Now, via our last video, as you should remember, T1 is pulling on mass 1 to the right and mass 2 to the left. So I might as well put those in right now. The third question that is usually asked is to actually find this tension. So I'm going to show you how to do this with variables. And if you could do it with variables, whatever numbers you were given will not matter. If you could do what I'm showing you today, then the numbers are going to be the easy part. Now I'm going to make a few assumptions here. I'm going to assume our givens are as follows. We know force X, we know mass 1, and we know mass 2. So these are my givens. For now, I'm going to assume this is a frictionless situation. We're going to do this twice, one without friction and one with. Now, here are my steps. 1, define your system. So define what you are concentrating on. 2, make a second law equation for your system. This one should look familiar because you have seen it before. And you've seen it before because it is a very important technique to know and understand. 3, redefine your system to find tension. So identifying what your current system is very important. I'm going to show you how to do it. For starters, to define your system, typically you will outline it. So what do I want in my system? Well, I want these two objects, but I do not want the ground. So I'm going to identify that with a dashed line. So everything in the dashed line is in my system. I have mass 1, mass 2, the rope is in my system as well, but notice the ground is not, because I am not finding anything about the ground. I want the acceleration of the system, and I want to know tension 1. There's actually a more important reason why we didn't include the ground, but it includes friction, but that is going to be for the second part of this problem. All right, now that I've defined my system, I'm going to put on whatever forces I know. I'll start with mass 2. I have force Earth on mass 2. Then I have force normal on mass 2. I also have, of course, force Earth on mass 1 and force normal on mass 1. And there are no frictional forces. So now I can do step 2, which is create an acceleration equation. Acceleration is F net over mass. Now, for starters on the y-axis, my force normals and force Earth all cancel. So these two cancel and these two cancel. I don't have to worry about the y-axis. Let's look at the x. On the x, I have force x to the right. Now, the only other horizontal forces I have are from tension 1. Right here, I have tension 1 going to the left, so that's negative T1. And right here, I have tension 1 to the right, which is positive T1. So, guess what happens? So what happens? Well, as you can probably see, the tensions cancel. Tension 1 is pulling on mass 2 to the left, so it's negative. Tension 1 is also pulling on mass 1 to the right, so it's positive. Since both ends of this rope are in my system, these two forces cancel. They are third law pairs. They're in opposite directions and they have to be equal. It's as if you put your car in neutral, got in it, put your hands on the dashboard and put your feet in the back seat and started to push. The car wouldn't go anywhere because your hands are pushing forward and your feet would be pushing backward. So to finish this, my system includes mass 1 and mass 2. So my acceleration equation would be force x over mass 1 plus mass 2. Now, since I have force x, mass 1, and mass 2 as my givens over here, that means I now have acceleration. Acceleration can now be added to my givens. The next question up is, how do you get tension 1? Well, I can't use this equation because tension 1 cancels. If my system includes both sides of this rope, these forces will always cancel, which means I now have to redefine my system. And what you want to do is define a system that cuts this tension in half. I will do that by isolating mass 1. So now, this is my new system. I will again make an acceleration equation for this new system. I'll call it acceleration 1 because it's of mass 1 equals F net over mass. Now the net force on mass 1 is tension 1, positive because it's to the right, over mass 1. That's the only mass in my system. Therefore, if I rearrange for tension 1, it'd be tension 1 equals mass 1, acceleration 1. Now, here's the key. This acceleration is for the whole system. If I pull mass 2, mass 1 comes along with it. So this acceleration is the same, which means we have mass 1, it's in my givens, and we have acceleration, because this acceleration is the acceleration for the entire system. This would also work if I cut the other side of the rope. So in other words, if I made this my system, just mass 2. So notice I'm still cutting the tension in half. I make an acceleration equation. I'll call it acceleration 2 because of mass 2. Now net force is right minus left. Right, I have force x minus tension 1 over mass 2. Therefore, tension 1 equals force x minus mass 2 A2. And again, we have force x, we have mass 2, and we have the acceleration because, again, we already found the acceleration of the system. Once you get the acceleration of the system, that's the key. And this would solve for T1, and this would solve for T1. If you're a little rusty on the algebra, make sure you understand how I got from here to here. But again, first, I define my system. I make a second law equation for the system. 3, redefine your system. And notice after I redefined my system, I went back to 2 and made a second law equation for my new system. So the idea is you do this as many times as you need to until the problem is over. Okay, so I'm going to do this again with friction this time. So givens, we have Fx, mass 1, mass 2, and mu, the coefficient of friction between the ground and the blocks. It is assumed to be the same for both of them. So 1, once again, I'm going to outline my system. And again, I'm outlining the same thing. Now, it is really important now that I did not include the ground in my system because of friction. The force of friction on these two blocks is going to be to the left. So I'll actually put them on here now. This is force friction 1, and I'll put force friction 2 here. If the ground is exerting a force on the blocks to the left, the blocks are exerting a frictional force on the ground to the right. If I included the ground in my system, these forces would cancel. So we do not want to do that. The goal is to find the acceleration of the blocks and tension 1 again, which means we do not want to include the ground in our system here. So let me complete these forces. Force earth on 2, force normal on 2, force earth on 1, normal on 1. Tension 1, again, is pulling to the right on mass 1 and pulling to the left on mass 2. So notice I have two forces here right next to each other. Let's make our acceleration equation. Acceleration is F net over mass equals. So we're going to take a look at forces to the right. I have force x to the right Now, I'm not even going to include tension this time because I know they cancel. This side and this side cancel out. However, I have two frictional forces, minus force friction 1 minus force friction 2, because they're both to the left, over mass 1 plus mass 2. I now need to expand this. Force X minus friction by definition is mu times force normal. And in this case, that would be mu m1g minus mu m2g, m1 plus m2. This is because force Earth is mg. This is horizontal ground. There's no acceleration on the y-axis, so force normal is also m1g. Same thing with mass 2. Okay, now again, we have all these. Force X is a given, so is mu, so is mass 1. We know g, it's a constant, so is mu, mass 2, g, mass 1, and mass 2. We know all this stuff, which means, again, we essentially have the acceleration. It is now basically a given. Once we have the acceleration, our next goal is to isolate tension 1. And now that we have acceleration, we can use it. So again, I'm going to isolate mass 1. Side note, if you notice from the last problem, you typically have a choice. You don't have to do both. I'm showing you both just to show that you can. But if you notice, the math for mass 1 is a little cleaner. Acceleration of mass 1 is F net of 1 over mass 1 equals, I have tension 1 to the right here, minus force friction 1, which I'll simply write as mu m1g over mass 1. Therefore, tension 1 equals mass 1 times acceleration plus mu m1g. Here is T1 isolated. Side note, I am leaving acceleration because we have it. This is the acceleration in base terms. Whatever you're given are considered the base terms. I have acceleration in base terms, so I am now using it. On the AP exam, they will probably want tension 1 written entirely in base terms, which means you literally have to substitute what I have up here in for A. So just to show you, I'm now going to isolate mass 2. Again, I got tension 1.5. Acceleration 2 is F net of 2 over mass 2. F net on 2 is force X minus force friction on 2, which is mu m2g minus tension 1, because tension 1 is pulling to the left, over mass 2. Therefore, tension 1 equals Fx minus mu m2g minus m2a. And again, this works because this is the acceleration of the system. It's the first thing we found. Once I found the acceleration of the system, that is the acceleration of mass 1, and that is the acceleration of mass 2. They are the same value, which is why I can now use it here. One of the best things you can do for yourself right now is to literally make up numbers for these. Fx, mass 1, mass 2, and mu. And I recommend keeping mu between 0.2 and 0.8. Then find the acceleration. Then find tension 1 using both methods, and you will see that they equal each other. But it would be very good for you to go through the entire process yourself. Just watching this video is not going to help you. We actually need to do it. And on the side, if you happen to get a negative value for acceleration, that is perfectly fine. Okay, so this is the technique to solve a multi-object system. Next video I make are going to be more complicated systems. This was the basic one, but once you get the technique down, the technique is the same every single time. The technique: 1, define your system. 2, make a second law equation for your system. 3, redefine your system, define tension. After you redefine your system, you're going to go back to step 2 and make a second law equation again. And when you redefine your system, you need to slice that rope in half to get one side of the tension, but not the other, so it does not cancel anymore. That's the key. All right, I hope this helped you out. Have a good day. This is Mr. M signing off.